In this video, we're going to do the solution to the first example at the end of the first derivative test. So we want to find all local extrema of 3x to the fifth minus 5x cubed. So I already started the first two steps of this and had some camera issues. So we're going to start this the same way that we did the last one, which is find the derivative of our function because we want critical values. All right, so the critical values of your function are the candidates for local extrema. They're not necessarily the answers, but they're the candidates for the answers. So I took the derivative of my function, and then now I want to consider the two different types of critical value. So x can be a critical value if it makes the derivative not exist, or if it makes the derivative 0. This case is very rare, and I think we may not have even seen an example of this yet. But the very last example in this section has it, so you can see it in action. So here, this is just a polynomial, so this just isn't an issue. So the only place that we're going to get critical values are from where your derivative equals 0. So I'll set my derivative function equals to 0, and I want to solve this for x. So the easiest thing to do here is to factor out kind of the common factor here. So both of these terms have a 15, and then both of these terms have at least two x's. So I'm going to factor out 15x squared and leave x squared left here, and then there's just a 1 here because that was everything. So if I distributed this term in, I would end up with the line above. So anytime you have something set equal to 0, the first thing you should check for if there's common terms like this. So I'm going to go one more step. X squared minus 1 factors into x plus 1, x minus 1. You can learn that as a trick. You can use regular factoring, or you could have gotten those numbers from the quadratic formula. There are lots of different options for that last step. All right, so if I set this equal to 0 and solve, I get x equals 0. If I set this x plus 1 equals to 0, I'll get x equals negative 1. And then if I set this equal to 0, I'll get x equals 1. So these three numbers are my critical values. Okay, so now we're going to take these critical values and move on to the second step, which is testing your derivative kind of in the intervals between. So I'm going to make myself a number line with lots of space, and I'm going to mark all three of these in the correct order on the number line. So if 0 is here, negative 1 would be here, and 1 would be here. So we are going to get, we have 1, 2, 3, 4 different sub-intervals to be concerned with. So we have to test for different values. So I like to write f prime next to this before I start to remind myself that's the function I'm plugging into. So I know that f prime is 0 at all three of these, and in between I just want to see if it's positive or negative. So the reason that we can just pick random numbers in between to test is because these are the only three places where your derivative could change sign. So if somebody in here, let's say, is positive, its derivative is positive, there's no way it could change sign until negative 1, so we know that this whole interval would have a positive derivative. All right, so let me switch colors to make this a little bit more clear. Okay, so let's pick any number to the left of negative 1, let's say negative 2. So I want to plug negative 2 into my derivative function, which is this here. So you can use this format, or what I actually really like is using the factored format here, 15x squared, x plus 1, x minus 1. So the actual value of f prime of negative 2, the actual number that this is exactly, I don't really care. All I care about is whether it's positive or negative, so you can sometimes kind of take some shortcuts from the factored form to figure it out. So what you can do is either plug negative 2 in here and just throw it in your calculator and get a number, or we could say, all right, 15x squared, that would be positive because it's squaring. Negative 2 plus 1 is negative, and then negative 2 minus 1 is negative. So this will come out to a positive number. I'm going to say positive here. All right, so this is the way I like to kind of cheat through it without as much computation. If what I did you really hate, don't do it. Actually just plug -2 in, use your calculator and get an answer. Okay, so here we've got to pick something between -1 and 0. -1/2 will do it. And again, I'm going to use my cheat method. You're welcome to actually plug in -1/2 and get a number here. So the squared part will definitely still be positive. It'll be positive for everything if it's squared. -1/2 plus 1 is positive. -1/2 minus 1 is negative. So altogether, this will come out to be a negative number here. Okay. Now this third interval here, I want to plug in a number between 0 and 1. So I'm going to pick 1/2. But again, any number between 0 and 1 will have the same kind of punchline. All right, so that's going to come out positive, then negative. So I'm going to get negative here. And then finally, we'll plug in one last number into this fourth interval. Any number bigger than 1. So you could plug in 2, you could plug in 100. They should all give you the same sign, which is what we care about. So I'll do, let's say, f prime of 2. That'll be positive, positive, positive. So this will come out positive. Okay, so what this is telling us, we'll get rid of all these colors. What this is telling us is that my derivative is positive, then negative, then positive. So the original function f is going up and then down. Something happens here, but then it keeps going down. And then it goes back up, right? So we have up, down with maybe some sort of squiggle, and then it comes back up. So right here, because it went up and then down, we have a max at -1. At 0, the derivative did not change sign, so at 0 we have neither, which happens sometimes and is cool. And then at 1, f was decreasing and then increasing, so what we have is a min. So let me organize my thoughts here. So I have a local max at x equals -1 and a local min at x equals 1. So I'm going to ignore 0 from here out. Because of how the question was phrased, it just said find the local extrema. So now 0 is not, one of my important numbers, so it's by the wayside. If the question says like identify or label all the critical values as a max or min or neither, then you would specifically list it as a neither down here. All right, so the very last thing to do, because the instructions ask for the xy point, we have that extra step where we want to get their y values. So we're going to plug 1 and -1 back into the function. So here we need f of -1, and here we need f of 1. And this is back to the original function, 3x to the 5th minus 5x cubed. Okay, so if we plug in -1, I'll press fast forward here, we should get a 2. And if we plug in +1, we should get -2. So we have, as our final answer, 1 local max at -1, 2, and 1 local min at 1, -2. That is my final answer.